All right, so in this video, I'm going to be going over everything you got to know for a significance test. So if you got like a test in like an hour or half an hour, this is the video for you. So let's get going. Ready, Pepe? Yeah. Okay, so significance tests all start with your HO. You know, your null hypothesis, HO. And the HO is always against your HA. You know, your alternative hypothesis, HA. So let's go over an example. Let's say like I'm just hanging out after school after a long day of work. So I go out and shoot some b-ball, shooting hoops. And out of the out of like the bushes or something comes some like punk. He's like, yeah, you suck at basketball. He insults me or something. I'm like, I don't really care about what you're saying, I don't care. He's like, well, I'm better than you. I'm like, what? He's like, I can shoot. I can shoot better than you. I can shoot 90% from the free throw line, he says. And I'm like, okay, I don't believe you. He's like, yeah, well, I'll prove it. I'm like, all right, prove it. Let's see what you can do. Even though, I just hope he would just go away. But I give him my basketball. He doesn't really catch it, but he eventually holds on to it and shoots, 50 shots. 50 shots. And he makes 20. He makes 20 out of the 50, which is 0.4 or 40%. But he claimed that he was a 90% free throw shooter. That's what the null hypothesis would be. He's claiming that P, his proportion of making free throw shots, is 0.9. And I'm like, no. No way, you suck, man. I can just tell by looking at you. So I'm saying that the true proportion is less than 0.9. I'm not like, you don't have to give a specific value for the alternative hypothesis. You have to say it's not equal to that, greater, less than. In this case, less than. And so he shot 20 shots, or he shot 50, only made 20. And this is a sample proportion. Because technically, he only shot a sample, or only some of the shots he's going to shoot, probably in his whole life. The population of free throw shots is going to include all the free throw shots he takes his entire life. So he just took a sample, and that sample showed that he made 40% of them. And then so I'm like, yeah, see, that's evidence. You freaking suck, man. And he's like, no, well, he's like, I'm having a bad day, man. I just got hit by a car, and I broke my arm, and all this stuff. He got chased by a squirrel or something. He's making excuses, and he says like, I'll come back another day. I'm better. I'll shoot better. And I'm like, dude, man, 40%. That's not even close. And now I'm like, thinking, well, like, how close does it have to be for it to be like, arguable that he is having an off day? Because yeah, it's possible. It is possible. It's possible, that pigs can fly. I saw a Simpsons episode once where pigs are flying, or just one. But it's probably really rare. So how rare is this? If he's actually a 90% free throw shooter, if his true proportion of free throw shooting percentage is 90%, what are the odds that he would shoot 40% from a sample of 50 shots? So we want to figure out this probability. This is called our p-value. The p-value will tell us what the odds are of him shooting for 40% if he was actually a 90% free throw shooter. Now, before we do a significance test, we have to have like a limit. And we have to say, well, okay, well, if the odds of this happening is less than 1% or less than 5% or less than 10%, then I'm calling BS. You have to claim that. You have to claim what percentage you're willing to work till, because if you say it after, then it's gonna be biased. So in other words, you have to claim what's called your alpha level or your significance value. Usually, by default, if it doesn't say like in a problem or just generally in life, 5% is typically what the average significance level is. Meaning that if the odds of this happening is less than 5%, then we're going to say, okay, looks like you suck at free throw shooting, you're lying. So if the p-value is less than 0.05, we do what is called, we reject HO, you reject the hoe. And then you're going to say, yeah, I'm going to accept the HA. But if the p-value we get from this, if we get the p-value to be 0.05 or greater, then we say we failed to reject HO. Failed to reject the hoe. I mean, our null hypothesis. Now, we don't say we accept it. It's kind of like, in court, you say guilty or not guilty. We fail to reject it because, I guess we could say there's some chance that, he did have an off day. So those are two conclusions we can make. Now let's go through a formal example so you guys get like a real step-by-step, full response problem so that on your test you know exactly what to do to get a full grade. So let's turn our attention to, all right, so we're going to work through this problem here where we got the flu vaccine. This is a drug company has developed a new vaccine for preventing the flu. Good for them. The company claims that fewer than 5% of adults who use its vaccine will get the flu. To test the claim, researchers give the vaccine to a random sample of 1,000 adults. Of these, 43 get the flu. Okay, so do the data provide convincing evidence to support the company's claim? And we got to figure out whether we could have made a type 1 or type 2 error after we run a significance test. All right, so let's get going. Let's switch back to the whiteboard actions. All right, so again, we start with our hoe. So our null hypothesis is going to be that the true proportion P of people that get of adults that get the flu when using the vaccine is 5%. And the alternative is that the company's claim that the true proportion of adults who use their vaccine will be less than 5%. It's be less than 0.05. Now, we now have to break this into a calculation where we want to calculate standard deviation and basically what the odds of getting this sample proportion here. So we had 43 out of 1,000. So our sample proportion is 43 out of 1,000, which is 0.043. So 4.3% of those people that took the vaccine and their sample got the flu. So we're basically thinking like, well, that is less than 5%. So they're gonna be like, yeah, see, our vaccine works. Look at that. Less than 5%. And we're like, well, hold on, man. Maybe they're just in good health. Maybe these guys are like, fitness, savants, and they're always, working out and taking vitamins, and you're like, no, those people are unhealthy. And we're like, okay, let's just test it. So we have to see what are the odds of getting a sample proportion this low or lower if the true proportion is 5%. So we have to run a calculation dealing with a significance test or one sample. Depending on how your teacher wants you to format it, we do a 4-step problem and usually state what you want. We'll state the type of inference method you're going to use. So z-test, remember that ZAP-TAX, one sample z-test for proportion for P. And you got to check 3 conditions. Remember the random, 10%, and then the large counts. The random condition is sample random. It says it's Yeah, random. They got a random sample of 1,000 adults. So yeah, 10%. Is this sample no more than 10% of the population? 1,000 is definitely less than 10%. There's like a couple of billion people in the world, but we don't even need to go to that less. But what we're checking here, just to write it formally, 1/10, or our sample size, our n, our small n, is less than or equal to 1/10 of our large n. In other words, 1,000 is definitely less than 1/10 of n of the population. So there are at least 10. Well, let me just finish writing. There are at least 10,000 people in the population. Yeah. Large counts. P naught times n is at least 10, and P naught, or 1 minus P naught times n is also at least 10. Now, understand that both these are just opposites of each other, meaning that whatever one, that both these are going to add up to 10, or add up to the sample size, but let's just do it. So our P naught, our null hypothesis proportion, is 0.05. So we're going to do I should write this neater. 0.05 times 1,000. Is that at least 10? Yes, because that's 50. 50 is at least 10, so we're good. If this is 50, that means this is going to be 950, because they have to add it to 1,000. And I'm kind of, rushing and messy, and being messy in that part, because that part's not too important. Your professor or teachers aren't really going to place too much emphasis on scoring this, unless they're kind of like being an asshole or something. But now the next part is key. So I'm going to erase this so I can write this clearly. You're going to calculate your test statistic. Your test statistic, your z-score, is going to be equal to p hat minus p naught over the standard deviation of this. Now you get this in your formula sheet, so don't freak out about having to memorize it. I've been doing this for thousands of years, so that's why I just know it. But just make sure the calculation is run right. So looking at okay. So doing the math, you will get 0.043 minus 0.05 over 0.05 times 0.95 over 1,000. Make sure you don't mess up on this calculation, because that'll screw you over. So double, triple check it. Make sure it makes sense. So you should get, let's see, 0.043 minus 0.05, negative double 0.07 on top. I'll show the work, because I know my students like it, because sometimes some of them will still struggle with algebra. But that's on them. But I'm just being nice sometimes. 0.007 divided by 0.0068920,244. So down here you should get about 0.0068920,244. 920-244, and you'll end up with approximately negative 1.016. Okay. Now, what the hell does this mean? You use it the same way that you use a z-score back in like chapter 1, chapter 2 of stats. So you're looking at a normal distribution because you standardize it. You've made it into standard or a standard z-score where the mean is 0, standard deviation is 1. So we're looking at the area to the left of negative 1.01. So this is like negative 1.01. So we're looking at this area. This area will be the probability of getting a sample proportion of 0.043 or lower. So we can just use our normal CDF function. Normal CDF and negative a billion, lower bound, comma upper bound, negative 1.01. We get 0.1562. So the area here is about 0.1562. So the probability, well, I'll write it in case you forget how to do this in your calculator. You can just do the normal CDF function. Remember, it's your lower bound, so negative 1,000. Does that appear on the screen? Not that cool. I got you. Normal CDF. Get this chair out of the way. Lower bound is negative whatever, 1,000. Upper bound will be the negative 1.01. If you need it. You can always use your yellow sheet, but come on. Now, what this is saying is that the odds of getting a sample proportion of 0.043 or lower is about 15%. That's too high, man. That's these companies, we gotta turn them down. We gotta tell them, your vaccine ain't that impressive, man. We can get those 4.3% of people, logging, the flu 15% of the time by luck. And you're like, man, what the? We're like, sorry, bye. So let's put that in a nice sentence frame. So I'm gonna fast forward and that was tiring. Here we are. Let me put this in red. So since our p-value of 0.15 is higher than our significance level of 0.05, we fail to reject our null hypothesis. We do not have convincing evidence that this vaccine actually helps to reduce your chances of catching the flu. So, remember, if it doesn't give you a specific alpha or significance level to use, go with 0.05. All right, so the follow-up question is saying, what type of error could we have made? A type 1 or type 2? So let's finish with that. That's perfect. So we could have made I'll give you a hint, it's type 2. So type 1 error, you can make a type 1 error if you reject HO. It's possible to make a type 2 error only if you fail to reject HO. L2. So first thing you just have to memorize that. A simple way to kind of remember is type 1 error could occur when you reject HO. A type 2 could be when you fail to. So think fail to. That'll help you remember. Now, so what does that mean? This is where you have to think. I got like a bug bite or something. This is where you have to think logically. Because remember, we failed to reject HO, so we could have made a type 2 error. So in other words, you have to think about what mistake could we have made, meaning that we concluded that their vaccine doesn't help. But we could be, mistaken. Maybe their vaccine actually does help. So the mistake is that we believe that the vaccine doesn't help when in reality it does. That's all there is to it. So don't overthink it, because these type 2 errors could type 1, type 2 errors can drive you crazy if you just don't keep it simple. Remember, it's always possible that you could come to the wrong conclusion. So just think about the opposite of what you came to. So we came to the conclusion that the vaccine doesn't work, but we could be wrong, meaning that the truth could be that the vaccine does work. That's it. So there you go. Hope that helps. See you guys, next time after you ace that test or whatever. All right, say bye, Pepe. Hell yeah, bye. All right, thank you guys. Make sure you subscribe, and I'll catch you when I see you.